Hello and welcome to my analysis of Lab 2 Projectile Motion. The purpose of this lab is to study projectile motion under the force of gravity only and then that same motion including the drag force. This lab relies on the Newtonian model of physics, which is made up of three underlying physical laws. A body at rest will remain at rest unless acted upon by an external force. Force is equivalent to mass times acceleration, and every action has an equal and opposite reaction. And this specific lab also relies on the principles of projectile motion. In an ideal system, the only force acting on a projectile is gravity, so the x velocity would be constant. But in real life, drag also acts on a projectile, so neither the y nor the x velocity is constant. And below is shown the equation which solves for the drag force. A quick introduction to the results shows that the model that included only gravity does not line up very well with the observed motion, while the model that included gravity and air resistance is nearly identical to the observed motion, which is collected using tracker. This shows that physicists must include drag force in their calculations when trying to make accurate predictions of projectile motion. Below are shown some of the physical equations that I used to solve for the net force acting on the object, the velocity update formula, and the position update formula, all based off of Newton's second law of motion. For this lab specifically, the system was a paper ball and the surroundings is everything else. Now, using tracker, I was able to move frame by frame and measure the position of the paper ball. A reference measurement is needed to calibrate the software so it knows how far the object is moving, and the time scale must also be calibrated based off the camera's FPS so it knows how much time is changing between each frame. Now, I uploaded a video that showed a paper ball being thrown in an arc that captured the perspective which showed motion in the x and y axes, and the initial conditions are shown below. And it's also important to note that an unknown drag force is acting on the ball, which will be calculated later. Now, using the glow script computations, I had to manually set the initial parameters, and I set them to be the same as the experimental conditions that we saw in tracker. But now I have the option to include drag force or not to include it based off how I code the model. And so I ran two different versions. Now, this code relies on the Newton's second law to derive the velocity update formula and the position update formula, and an iterative loop records the final position over a given time interval through small steps, so I was able to track the motion over time. On the left hand, you see the motion, which included only gravity acting on the ball. It turns out to be a very symmetrical parabola. On the right hand side, you can see the motion when drag is included, and you see an asymmetric parabola that didn't travel as far as the model with only gravity traveled. This is because the drag acts opposite to the velocity, slowing the object down over time. Now, what does it mean? Well, terminal velocity occurs when an object is falling with a net force of 0, and this happens when the drag force and the force of gravity cancel each other out. The model does not show an object that has reached terminal velocity. This is seen by the velocity versus time graphs, which always have a non-zero slope. If we had reached terminal velocity, the velocity would be a flat line with no slope. For the object to have reached terminal velocity, it would have needed to be a lot more vertical space to fall. Eventually, the horizontal velocity would be reduced to 0 by drag, and then the drag force would cancel out the force of gravity once the velocity in the downwards direction got high enough. Now, this graph shows the modeled projectile motion under just gravity has a wider trajectory compared to the observed motion of the paper ball. The modeled projectile motion, which accounted for air resistance, however, was nearly identical to the observed motion of the paper ball. These results indicate that air force has a noticeable effect on projectile motion in the real world. When drag is not accounted for, the ball travels much further than it actually would have. When drag is accounted for in the models, the predicted motion lines up almost perfectly with the observed motion. And the coefficient of drag was calculated to be about 2, which is calculated from the gross script model. Now what if? If the paper ball were thrown straight up, it would result in more airtime, and this is because air resistance acts based off an object's total speed, not just the velocity in respective direction. When a ball is thrown at an angle, it has a higher total speed even if its vertical velocity is the same. This results in a higher drag force, and therefore the ball thrown at an angle has less airtime because it's being acted on by more drag. Now, what can we conclude? This lab showed that computational models are extremely accurate when predicting the motion of an object under projectile motion. It is always important, however, to understand the initial conditions and external forces an object is subject to. In this scenario, drag force played a crucial role in being able to predict the motion of the ball. Without an understanding of drag force and the equations to calculate it, physicists would not accurately predict the projectile motion. Thank you.